Hermitian forms. Okay. And as we will figure out soon, that they're not at all harmful. Okay. Rather, they're quite useful in extending the concept of length or the concept of inner product, real vector spaces to complex vector spaces. So, by a Hermitian form, we mean a bilinear form on a. So, let V be a complex vector space and define, well, we are not defining something, we are just defining the properties, and let this be the form from V cross V to C such that 1, this is conjugate linear in first variable, that means CVW is equal to C bar VW for all C in C. Okay. The second is that it is linear in the second variable. Okay. So, that is C, this is W, yeah. So, VW is, well, V times CW is equal to CVW. So, just the scalar multiple comes out. Let me write it clear. Okay. For all C in C. And of course, it is not only the scalar multiples which are coming out, also in the first variable you have say 1A V1 plus V2 W is equal to V1 W plus V2 W, and 2A, that is V W1 plus W2 is equal to V W1 plus V W2. Okay. So, you can make it together just by writing that, or summation say AI Vi, I running from 1 to n, some linear combinations, j running from 1 to m, say Bj Wj, this would be summation I running from 1 to n, summation j running from 1 to m, and then what will happen? The terms, yes, right. So, AI bar Bj Vi Wj. Okay. And there is one more property which is coming, I mean, except 1 and 2, that is the conjugate linearity in the first variable and linearity in the second variable. There is a third one, it is called Hermitian symmetry. Okay. Which is VW is equal to WV bar. Okay. So, the conjugate of this one. Okay. In particular, you can write this as well as summation I running from 1 to n, summation j running from 1 to m, AI bar Bj Wj Vi bar. Yes, sure. Yes. If C goes inside, okay. If you take it back inside the inner product, you multiply it with the second thing. you just multiply it. It doesn't matter, it's equal, right? By definition, that is C times VW is equal to C bar VW, and this is also equal to VCW. Okay. So whichever way you want to multiply it, I mean whichever argument you can. Okay. So these are Hermitian forms, and then we must define what is the standard Hermitian form. That is our first example. Say standard Hermitian forms. That this is just a particular kind, I mean particular vector space and a particular form. Okay. So just an example. Okay. So take V equal to Cn and define x, y, where x and y are elements of Cn. So that is, say, column vectors in Cn. This is just x bar transpose y. Okay, and this is the standard Hermitian form. Excuse me. Yeah. Okay. Now for this one, bar transpose, we will introduce a shorthand notation. Okay. That's star. Okay. Let's write it down here, and then we write it once more there. Okay. So here x star, we are defining it as x bar transpose. Okay. Okay. This one would be called adjoint. Okay. And we do not only define it for column vectors or row vectors, we define it for arbitrary matrices. Okay. And this is going to be useful soon. Adjoint of a matrix. Okay. So let A be an element in M N C. Okay. Some m cross n matrix with complex entries. Okay. Define the adjoint of A as A bar transpose. Okay. In particular, we have A B star is equal to B star A star. Okay. Because when you take bar, it's A bar B bar, and then you take the transpose, say, and you know that A B transpose is B transpose is transpose, right? Also, a double star, that is, you take the bar transpose once and you take the bar transpose once again. What you are going to get? You are going to get A back, right? So this is this. Okay. And this is true for any matrix A. Okay. Now, let's define another concept which is called self-adjoint or Hermitian matrix. Okay. We'll say that they are very much related with Hermitian forms. Okay. So these are just the matrices. Well, A in NC now, that is n cross n matrix A with complex entries, such that A star is equal to A. Okay. That is, you take the bar transpose of A, you get A back. Okay. Now here we would like to give you a few easy to do exercises. Exercise 1, if, well, let from V cross V to C be a, well, what you would like to say, that the matrix is, well, given a form we will have a Gram matrix, right? That is, actually a form is uniquely defined by its, I mean, given a basis and a form, all you have to do is to define the form over the basis and you are done by linearity or by conjugate linearity, depending on the definition. I mean, whether you are taking a Hermitian form or whether you are taking some other kind of form. Well, no, what I want to say is that you are given the form, right? So once you are given the form and you know what kind of form it is, you can actually get the, I mean, the values over the basis. Okay, and once you have like n square elements in the field associated with vi vj's in the basis, by linearity or bilinearity or conjugate linearity on the first variable, linearity in the second variable, you are done on the entire space. Okay. So now let this be a form, then this form is Hermitian if and only if the Gram matrix of the form with respect to any basis of V is Hermitian. Okay. And the proof is exactly as we have done with symmetric forms, and we have shown that the Gram matrix is symmetric if and only if the form is symmetric, right? Just the same argument works. Sairam. Yeah. No. It's just a Hermitian form, and that's a Hermitian matrix. I mean, the Gram matrix. So this is Hermitian if and only if the matrix is Hermitian. Okay. And the second exercise, it's about change of basis. Okay. Let G be the Gram matrix of a Hermitian form with respect to a basis B of V, and let B dash equal to BP be another basis of V. Then the Gram matrix with respect to B dash is not a kilogram matrix, but just a Gram matrix of this form, P star G P. Okay. All right. So now let's pause for a moment and think why Hermitian form, why not symmetric forms? We work with Hermitian forms because this lets us extend the concept of inner products from real vector spaces to complex vector spaces. We are going to see that in a moment. Okay. In particular, since VV for a Hermitian form. Since this is equal to VV bar, that implies this is real for all V in V. I mean, say, so we are having a Hermitian form over some complex vector space. Even if this is over the complex numbers, VV, I mean, if you put the same argument in both the, so same vector in both the arguments of the form, you get that the output of VV would be equal to that of its conjugate. So in particular, this is real. And then talking about positive definite, positive semi-definite, negative definite, negative semi-definite forms makes sense. Okay. So now we are in a position to define inner product. Okay, but maybe a bigger board. Inner product. Okay. So let V be a real or complex vector space. That is, it is defined over reals or it is defined over the complex numbers. Okay. In the real case, if V is a real vector space, then we call any positive definite symmetric bilinear form on V as an inner product on V. Okay. And a real vector space with an inner product, we will call it an Euclidean space. Okay. Euclidean space is a real vector space with an inner product. Okay. In particular, the standard Euclidean space is Rn with the dot product. Okay. The standard Euclidean space is Rn with the dot product. Okay. Then comes the second part of the definition, that is, we said that Hermitian forms lets us Hermitian form let us extend the concept of inner products from real vector spaces to complex vector spaces. Okay. So now suppose V is a complex vector space then we call any positive definite Hermitian form on V and inner product on V. Okay. And then we call Hermitian space, or there is another name, it is called unitary space. We will later use unitary to mean some class of matrices, but for unitary space Hermitian spaces are also sometimes called unitary space, referred to as unitary space. Okay. So these are complex vector spaces with an inner product. And again, the standard Hermitian or unitary space is just Cn with the standard Hermitian form. Okay. So in particular, for inner products, we see that this is not only in R, but for this, if this is an inner product, then VV is in R and it is positive for all V not equal to 0. Okay. So we may define the norm of V as the square root of, now the question becomes why square root, why not cube root or nth root? So that is a small question for you. Can you please explain why we take the square root here and why not any other root? Yeah, it's in the reals, right? I think in the past few exercises in your analysis course, you have perhaps seen that given a real number, nth root a real positive nth root exists. Given a positive real number, a real positive nth root exists. So why we stick to the square root? Why not any other nth root? Yeah? Yes, of course, but how is it compatible? Yeah. Yes, but even more simpler. We define the bilinear form to be linear or conjugate linear on its arguments, right? So in particular, if you define this to be its length, then for sure you would like the unit vector to have length 1, right? In particular, if you divide V with its length, that should have length 1, right? So you have, for example, in the real case, this one, okay, sorry, you require that V by norm V, this should have length 1, right? Okay. So that would mean, this is not only for real cases, it's actually for any, also for complex cases, right? So what you get, this one comes out in the, if it is a bilinear form, if it is a bilinear form or Hermitian form, is there any changes in what comes out? It's real, right? So just this will be 1 by norm V squared, right? And here you will have VV equal to 1, okay? And that would mean that norm V would indeed be given by the square root, okay? So that's the motivation of defining this in this manner. Now, let us prove this, that the eigenvalues of a real symmetric matrix are real. Okay. In other words, a real symmetric matrix cannot have complex, well, real numbers are complex. What I want to say is that a non-real eigenvalue. Okay. So at first, let's see an example. Okay, consider the 1 cross 1 matrices. Well, it's trivially true. The claim is trivially true for 1 cross 1 matrices. Okay. Now let's consider the 2 cross 2 case. Okay. So suppose we are having this matrix A, C, B, B in M2R. Okay. And let's check its eigenvalues. Okay. So its characteristic polynomial of this matrix is t square minus a plus c t plus ac minus b squared, right? So in particular, its roots are a plus c by 2 plus or minus root over a plus squared minus 4 times this, okay, divided by 2. So half a plus c squared minus 4ac minus b squared. Okay. So this just gives a plus c by 2 plus or minus half root a minus c whole squared plus b squared. In particular, you are having a real number here in the square root. I mean, both are squares, so both are. I mean, this thing is non-negative, and therefore your roots cannot be not real. Okay. So both of the roots are real, and now looking at, I mean, first looking at 1 cross 1, then looking at 2 cross 2, and we think that perhaps we are going to do induction, but that won't work here. Okay. So rather, we will generalize the question. Okay. Instead of looking at real symmetric matrices, we will consider Hermitian matrices. Okay. So, the claim is that the eigenvalues of a Hermitian matrix are real. Okay. So, and if we prove this, in particular this follows, right. So, here is the proof. Suppose we start with some eigenvector of a Hermitian matrix. Okay. So, let x be an eigenvector of a Hermitian matrix A. All right. So, in particular, what does Hermitian means? A is equal to A star. All right. Now, we have started with an eigenvalue of a Hermitian matrix A. Okay, we not eigenvalue, eigenvector of an Hermitian matrix A. That in particular implies that Ax is equal to lambda x for some lambda, which is a complex number. A priori, we do not know whether it's real. Okay. So, here lambda is in C. Okay. And we also have A is equal to A star. Now, do this x star Ax on both sides. Okay. All right. What is this? This is just equal to, okay, let's write here x star, yeah. Okay. So, this x star Ax is lambda x. So, we just write x like lambda x star x. Okay. And here we have, this is indeed, this is Ax star x. Okay. Now, Ax is lambda x, therefore, Ax star is lambda x star, lambda comes out, okay. Not lambda comes out, it is bar transpose. So, lambda bar comes out, right. So, this is lambda bar x star x. Okay. So, lambda x star x is equal to lambda bar x star x. Now, only, I mean, if we know that this is not equal to 0, then we are done, right. And why it is non-zero? It is an eigenvector, okay, and this is a positive definite form. Okay. So, lambda minus lambda, lambda minus lambda bar x star x is equal to 0, and x is an eigenvector. So, x is not equal to 0, and hence x star x is not equal to 0. Okay. That would mean simply that lambda is equal to lambda bar. Okay. That is all that we require to prove. Okay. So, indeed we have that the eigenvalues of our real symmetric matrix are real. Now we are going to define what are orthogonal matrices. Do you still recall what was an orthogonal basis or orthonormal basis? Yes. Yes. Yeah. Right. One, right, for orthonormal basis. And orthogonal doesn't have that normalization um, clause. It is, yes, it's just Vi Vj equal to 0. So, and I mean orthogonal matrices, these are real matrices, sorry, real matrices whose columns form an orthonormal basis of real n cross n matrices, say, whose columns form an orthonormal basis of Rn. Okay. That is, this is a set of matrices in GLNR such that A transpose A is equal to what? Identity, right? Okay. So these are called orthogonal matrices. Okay. And a similar concept is there also in complex, I mean for complex matrices. So these are called unitary matrices. Okay. So this is the other notion of, I mean other use of the word unitary, except for unitary spaces. Okay. Unitary matrices. Also in number theory there is something called unitary divisor, but I mean that's also not connected with this one, this concept here. So let's define what is a unitary matrix. Okay. These are complex n cross n matrices whose columns form an orthonormal basis of Rn. Well, of Rn here I should have written with respect to the standard dot product. Okay. And here an orthonormal basis then with respect to the standard Hermitian, the standard Hermitian form, right? So all right. So these are matrices in GLNC. I mean there are any matrices, but this condition would enforce, for example here, that they are invertible, right? Now here what should be the concept? Yeah, right, perfect. So here U star U is equal to identity. So this we will call unitary matrices. Okay. by the way, why are we so obsessed over orthonormal basis? What? Yeah, it's yes, exactly. Yeah. So here's a theorem, an easy theorem. Okay, if V is okay, an Euclidean or Hermitian space with with an orthonormal basis, well, these two together we call an inner product space. Okay, so by an inner product space would mean either it's an Euclidean space or a Hermitian space. Okay. Okay. With an orthonormal basis, say B equal to V1 dot 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 Vn. Okay. Then for all V in V, we have V is equal to summation I running from 1 to n, and here of course Vi. What will the coefficients? Yes? No, 0 or 1 should be for the basis. Okay, but you are given an inner product. Use that. Perfect. Or Vi dot V. Okay. So this would be an expression for V, and why is this so? Why we have such a canonical expansion of V? That is, given the information that the basis is orthonormal, why can we write down the coefficients in such a nice form? Right? Exactly. Yeah. So yeah, the proof is then you are expanding V as a linear combination of these vectors. So let C1 dot 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 Cn in the given field, I mean in F, where F is equal to R or C, besides that this V is equal to summation Ci Vi, I running from 1 to n. Okay. Then consider this Vi, comma V. Okay. What it will give? It's just a inner product. Yes? No, Vi, comma V, you are now going to use this there. Okay. So your Vi, because you don't know whether it is R or C, so we are just working with this notation. Okay. Ci Vi, I running from 1 to n. Okay. What we are going to do, we are going to use linearity in the second variable that we have for bilinear forms as well as Hermitian forms, right? So let's change this dummy variable. It is just I running from 1 to n, but we could also write it as j running from 1 to n, because here we have some I, right? And this gives you what? Ci times Vi. No, not Vi. Yeah, right. Ci times Vi Vi. No, you are given I. J was the dummy variable. J was running from 1 to n. So only in the case where j and I are equal, this inner product survives. In every other case, it's killed. Okay. It vanishes, right? So that's why the ith component will remain. Everything else will be killed. Okay. And that means now you remember that this is an orthonormal basis. So what is vi 1, right? So this is equal to just Ci. Okay. So you have vi v, the inner product of that is equal to Ci. Okay, and that gives us a proof of this.